Okay, great. Cool. I think it's going to work this time. I was having an issue. Um, I think we're good. So let's see. Let's see. Partial pressure, Dalton's law of partial pressure, and collecting gas over water. Great topic. It's fun little problems to solve. They kind of come at you the same way. It's fun little chemistry problems, if you will. Let me share my screen. And hopefully it's here. Good. Okay, so the first thing I have pulled up here is part of your PowerPoint. And this is Dalton's law of partial pressure, as you see down here on the bottom, down here. And all this is stating is that when we take a gas with this pressure and another gas with this pressure and another gas with this pressure, and we mix those pressures, those gases, we have a pressure that is equal to all of these individual pressures added up together. Notice the volume didn't change, okay? And also, while I'm here, it wasn't something I was going to include, but remember that the pressure of this gas is going to, divided by the pressure of all three gases, will equal the mole fraction of that gas. And I say that because this equation is a great and very useful equation to have in your toolbox. All right. And it also goes to show that the number of moles of gas and the pressure are directly related. Okay. They have a very, very direct relationship. But if I knew I can use, I can use moles to get pressures and such. And that's just something to realize. But Dalton's law of partial pressure, very simple. If we add the individual pressures up, we end up with the total pressure. And that relates to this topic of collecting gas over water, which I don't know if we got to do this last year. I remember teaching it, but I don't know that we got to do the experiment in class. Probably won't get to do it this year either. But as you can see here, and I'm going to draw it in a minute when I pull up my notes, is here you have a flask. It produces this gas. The gas travels through this tube, gas collecting tube, and up here, and we trap it up above the water. Okay, the same thing is happening over here, okay, where this is your reaction, and the gas comes up through here, up here, and it collects up above the water. Same thing happening here, same thing happening here, okay? So let's go ahead and I'm going to just write, kind of maybe do a practice problem. Hopefully I'll make up my own numbers and those numbers will work well. All right, so I'm going to pull up a note, put it in Unit 3 notes, and I'm going to call this collecting gas over water. And it is mentioned in relation to Dalton's law of partial pressure because we're going to create a partial pressure problem. So here is our experiment that's going to collect a gas. We're going to have some HCl in here. Let's say that it is 1.50 molar. Recall that that is 1.50 moles. Moles of what? Moles of HCl per every 1 liter of solution. We may use that number, we may not. I might elaborate, I might not, okay? And let's say that we are going to drop a piece of zinc solid, this would be our aqueous, into that hydrochloric acid. And it's going to produce a gas. So we're going to set up a gas collection tube. All right. Put a rubber stopper in here. Sorry, I'm getting a little fancy. So fancy, right? Okay. And then over here, if I can do this, I'm going to have, this is what I would have you guys do in the class. I'll give you a bucket. And I'd say, okay, what I want you to do is I want you to put some water in the bucket. And you'd say, how much water? And I'd say, well, enough, but not too much, right? We don't want the water to go over and spill it. I would give you a graduated cylinder and you would fill it up with water. I'd say, fill the graduated cylinder up, fill it up. And then I would have you flip it over real quick in the water. And what you would then have would be a graduated cylinder full of water, right? And there would be a vacuum. It would be like a vacuum system. So the water's not going to come out of the graduated cylinder unless this bottom mouth of the graduated cylinder actually breaks the seal of the water. So there is pressure pushing down on here, okay? It's pushing down on here, and it's called the pressure of the atmosphere. It's the atmospheric pressure. This is how a manometer works. I brought it up in one of the last lessons. And then this is pushing up on here, right? So that this stays full, okay? Okay, now what we would do is we would have our little really rigged up device with some bent glass and some rubber tubing. And we would put that rubber tubing up into here. Okay. All right. And then we would allow the zinc metal to react with the hydrochloric acid. Okay. And that would be the solid reacting with the acid. And that would give us the zinc 2 chloride. Not 2, just zinc chloride, but that's not a big deal. Plus hydrogen gas. All right. So we would have a 2 right here. All right. I'm going to clean that up because I've been cleaning my house and my yard all day and I want to clean. I've been doing my yard work today. Housework. Okay. So here is our gas that is being produced. And it's going to bubble through here. Okay. It's going to bubble up here. And what's going to happen is, let me fix my eraser. It's going to, let me draw this back now. This is pretty useful. That gas is going to, oops, let me make it red again. That gas is going to sit up here. Okay. Now, this would be the hydrogen gas. Now, what we have here is not a pure sample of hydrogen gas, but there's going to be another gas present. And that other gas that's present is going to be H2O gas. It's going to be water vapor, right? That came from here. All right, so some of the water will have evaporated, simple as that. So what we have here is that we have what's called a mixture of gases. The gas we collected and the water vapor. So we have the Dalton's law of partial pressure, right? We have a partial pressure problem. Okay, so what we want to do is just simply state that the pressure of the atmosphere, and recall that's this pressure here pushing down, right? And I'll go there in a minute, is going to be equal to the pressure of the water vapor plus the pressure of the gas collected, right? In our circumstance, it's hydrogen. It can be whatever it is. So once, like I said, we have a partial pressure problem. Now, in order for this equation to actually be true, I would like to say that the level, this level of water here needs to be level with this level of water there. So maybe I should redraw or do some erasing of my water and put the gas. Here's some of my water vapor, and then we'll put some more of this gas in there. Okay, so these need to be equal is all I was saying, because then it is true that this pressure is equal to those two added up. Okay, now this pressure of the water vapor is going to be temperature dependent, okay? So it's going to vary based on the temperature that the gas is being collected at, or the temperature of the water. So I would have you measure the temperature of the water in class, all right? Typically, this pressure is typically given. It's usually provided to you. If it's not, you can always look it up, okay? And it's the vapor pressure of water is usually provided. You can always look it up, right? It is the vapor pressure of water at a certain temperature. Actually, I'm going to write it like this, because vapor pressure, we often just write PVAP. PVAP, H2O, at a given temp. And you can just look it up. So what we would do if we were in the classroom in the lab is, just say, what's your temperature? Let's look it up and see, what's the vapor pressure of water. I would just provide you with several different vapor pressures around the temperature of 25 degrees Celsius, because that's usually about where we are, okay? All right, so what we have is a Dalton's law of partial pressure problem. Now, I could solve for so many things. Let's make up some variables. Okay, so let's clean this up. Let's just do this and draw this again, now that you understand the scenario. I don't want to draw it again. I'm just going to use the original drawing and just, okay. So what I'm going to do is I'm going to look at this, right? And remember that this, for us, is a graduated cylinder. It could be a burette, like a glass collecting. It's called an eudiometer, but we don't have those. So we just use upside down graduated cylinders. But I could right here measure the volume of the gas collected, right? Because this itself is a graduated cylinder. So this would give me the volume of the gas collected. Now, some students get confused. Both gases, the water vapor and the gas you're collecting, are sharing the same space. So if the volume here is, say, 30.0 milliliters, then both gases, the hydrogen gas that was collected has a volume of 30 milliliters, and the water vapor that's present there as well also has a volume of 30 milliliters. So they're sharing the same space. The gas particles are assumed to not take up any space. We'll look at that in a different video, okay? So whatever this volume is here is the volume of the gas collected. So we'll say that we collected 30.0 milliliters of H2. We'll say that the total pressure for this is 1.02 atmospheres. That's pretty standard. And I'm making some numbers up, okay? Let's say that our temperature was 25 degrees Celsius. And let's say that the vapor pressure of water at that temperature is 29.8 mmHg. And I would like to say that this is made up. Okay, I totally made that up. Actually, what I would like to do is just look it up. So I'm going to have you bear with me, and I'm going to go, what is the vapor? Come on. What is the vapor pressure of water at 25 there? And okay, it's about this 23.8. All right, so let me get back to y'all. Oop, I hope we're all still together. Are y'all still seeing my screen? Yeah, okay. So what do we say it was 23.8? So it was close. Recognize that 23.8 mmHg. All right, and the question could be, I mean, I could ask you so many questions. I could say, what mass of zinc reacted? I could say, what volume of HCl was used? All right, so let's look at both of those, okay? Now I'm trying to get back to my, I want to see this screen. It's getting on my nerves. Okay. Okay, sorry, I'm just, the video is not there anymore and it's bothering me. Okay. 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 Can y'all see my screen? I need to know this. Okay, I'm going to assume that you can. I just can't. There, now I can. Sorry. Okay. Okay, sorry about that. Okay, so I think we have everything we need here. Now, notice right here, we've got building up. We've got a volume of hydrogen. We've got a pressure of the atmosphere. We've got a pressure of the water. We've got the mass of zinc, the volume of HCl. Okay, so the first thing we're going to do is we're going to find the pressure. And I'm going to use a word that you're likely to see that's somewhat sometimes confusing, of the dry hydrogen gas. And that simply means without the water vapor. Okay, so we'll take the PATM minus PVAP H2O equals pH2. All right, and we've got this. This is given to us at 1.2. This, this is in millimeters mercury, so we'll just go mmHg, and then remember that if you divide that by 760, you'll get atmospheres. So we'll just divide it by 760 in our problem here, and that will give us atmospheres. And if I do this, I'll get the pressure of my dry water. So I'm first going to go 23.8 divided by 760. That gives me 0.00313. 1.02 minus that answer gives me a pressure of hydrogen gas that's going to be 0.989 atmospheres. All right. Okay. Now I'm going to find the moles of hydrogen gas. I'm going to use that by using the ideal gas law. right? A couple things. You can only use the ideal gas law with a gas. That means I cannot plug zinc into here. I cannot plug hydrochloric acid into this. Students try to do that. Ideal gas law can only be used with a gas. It's the gas law. So my moles must be the moles of a gas to use the ideal gas law. And I'm doing the pressure of the hydrogen, remember? So I'm going to use my pressure of the hydrogen, and that's 0.989 atmospheres. I need the volume of the hydrogen. Oh, that was 30 milliliters. And we need that to be in liters. So 30.0 milliliters. And if we divide that by 1,000 milliliters per 1 liter, we will get our liters. And if that's going to give us moles of hydrogen, because our pressure is of hydrogen. Our R is going to be 0.08206 liters, atmospheres, moles, Kelvin. Temperature needs to be in Kelvin. I think we said it was 25. That will give us 298. All right. So let's go ahead and get our moles of hydrogen. 0.9, turn it on, 0.989. Goodness gracious. Times, what's that, 0.03 equals divided by parentheses 0.08206. Look at your screen, make sure you don't make a mistake. Times 298, close parentheses equals, I got number of moles of hydrogen gas equal to 1.21 times 10 to the negative third. Okay. All right, so we've got that. Why did I get moles of hydrogen gas? Because the question asked for moles, the mass of zinc. Well, that's, to me, a perfectly good stoichiometry problem. Right? So remember we had zinc plus 2HCl yielded our ZnCl2 plus hydrogen gas. This was a metal. This was a solution. This is going to be dissolved in the solution, and that's going to be released as a gas. Now, if I have 1.21 times 10 to the negative third moles of hydrogen, I can look at my stoichiometry and see that every 1 mole of hydrogen relates to 1 mole of zinc. And every 1 mole of zinc, good thing I have a periodic table right here, has a mass of 65.39 grams of zinc. So I've got that number in there already, times 65.39 equals, okay, small amount. So I must have used 7.9, okay, times 10 to the negative second grams of zinc. All right, that's an answer. And then I like this last question. I might lose, not really, but we haven't done this yet. And it says to find the volume of HCl used. And we're going to need to do that in milliliters because it's probably a small amount. Well, let's think about what we know. We know that we have the 1.21 times 10, 1.21 times 10 to the negative third moles of H2. We know that zinc reacted with 2HCl and produced some zinc chloride that is dissolved and some hydrogen gas that we collected. We know that this was 1.50 molar, and we need to know the volume of it. So let me show you how this is going to work. Remember that this is 1.50 moles of HCl per 1 liter of the solution. And it's important for you to write that out until this becomes really easy for you. All right, I think if it's not easy for you, that would be something that would help to make it easier, would be to write this out, okay? Because that's our conversion factor. That's in fact the conversion factor. This molarity is a conversion factor. Throw it in a T-chart. Okay, so we can, I could work from my zinc or I could work from my hydrogen. I'm just going to work from my hydrogen. 1.21 times 10 to the negative third moles H2. Let's look at our equation. It looks like this is a 1 to 2 mole ratio. 1 mole H2, 2 moles HCl. And then I can use my molarity and to get to a volume. Cool, right? 1.50 moles of HCl for every 1 liter of the solution. And the solution is the HCl solution. And then they did say that there's probably going to be a small number, so let's go ahead and put that in milliliters, all right? So 1.21 with an exponent of -3 times 1,000 equals, divided by 1.5, gives me 0.806 milliliters HCl would have reacted. So much we can get from our partial pressure and collecting the gas over the water, right? We have the partial pressure problem. We've got ideal gas law problem. We've got a stoichiometry problem. We've got a using molarity to get a volume problem. So such a great question, okay? And if I made a mistake on my math, I would appreciate it if you would bring that to my attention. You know, I don't think I did, but as I was working through, I thought, man, I hope I didn't make a mistake anywhere. That line doesn't belong there, does it? So sorry, I'm rambling now, and I'm going to let you go. I think that was about all I needed to say. Dalton's law of partial pressure collecting gas over water. Okay, I'm going to go enjoy my Saturday now. Bye. Stop. End.